Hello, everyone. Welcome to our global webinar series brought to you by Rockflow Dynamics. My name is Jessica Kalin from the RFD Calgary office, and with me today is Senior Reservoir Engineer Horacio del Campillo to present to you History Match using 3D Discrete Cosine Transformation in tNavigator. We would like to thank each and every one of you for joining us today. We are honored you're able to give us 30 minutes of your time for this webinar. These are new worlds we're navigating, and our RFD team is working around the clock to maintain and increase support for all of our clients. Despite the global changes, we continue to be there for you 24/7. During today's webinar session, all of our attendees' microphones have been automatically muted. Should you have any questions, please navigate to the questions pane within your control panel. At the end of this session, we will be addressing as many questions as we can, the remainder of which will be answered and posted online for your reference in the coming days. Additionally, this webinar is being recorded and will be uploaded to our RFD Europe YouTube page, as well as uploaded to your FTP folder on our support website. Should you be left with any other questions at the end, or if you have a suggestion on what you'd like to see in a future webinar, please contact us at the email address on your screen there, asktnav@rfdyn.com. Each webinar in this global webinar series covers a breadth of topics, from geomechanics to cloud computing to hydraulic fractures to well placement optimization. The complete list can be found right here. It can also be found on our LinkedIn page, as well as on the main GoToWebinar registration page where you signed up for this webinar series. Each of our webinars touch upon a different aspect within the integrated reservoir modeling process available in tNavigator. If you're interested in learning more about the complete workflow or would like to start a free trial, contact us at asktnav@rfdyn.com. Now for today, we're live from Buenos Aires, Argentina, and I'd like to introduce you to Senior Reservoir Engineer Horacio del Campillo.
Hello, Jess. Can you see it in my screen?
You're good to go.
Okay. Well, hello, everybody. My name is Horacio del Campillo, and I'm going to show you how you can use a different technique for history matching a 3D model. This technique is called 3D Discrete Cosine Transformation. The agenda for today, we are going to have a brief overview of the algorithm. Then we will see how to build this workflow in Model Designer and work with the permeability in order to parameterize this permeability, do some sensitivity analysis, then run the acidic history matching process, and do the analysis of the results in Model Designer. What we are going to use for this session, we are going to use Model Designer and another module that is called acidic history matching and uncertainty. So typical problems when doing history matching, first of all, is matching the model to a map. Sometimes we are not allowed to change anything in a map, and that's very time-consuming not to work with the maps for the history matching. Split regions to modify permeabilities. Sometimes it's unclear in advance how to select these regions. Sometimes the geological prerequisites for such splitting do not always exist. Loss of correlations between permeability and porosity when changing permeability. These values of permeability and porosity in different grid blocks are correlated. Independent changes of the values in the regions destroys these correlations. Relative permeability modifications in conflict with laboratory data. Sometimes we are not allowed to change scale data since we treat this data as hard data. And reducing the number of history matching parameters can help you a lot for accelerating the matching of the model. So using 3D cosine transformation can help reservoirs to keep the original scale data with no modifications. Also understand in a better way the absolute permeability distribution. And also is a very useful tool in addition to conventional history matching practices. So what is discrete cosine transformation? The algorithm is widely used in many areas where data compression is required. For example, in this case, we have a picture, and with the algorithm, we reduce the size of the resolution of the picture. But at a simple view, we have almost the same picture. This discrete cosine transformation helps separate the image into parts of different importance with respect with the original image. Other popular use is MP3 audio files. So when we apply this 3D cosine transformation to a grid property, we end with a formula like this. This applying to a 3D grid, we end having a complex formula with these coefficients equals to the number of grid blocks. And we have to ask ourselves, how many variables do we need and how we can reduce these numbers? So for this, we have to define how many grid blocks we want to use. We need to resolve the problem in a way to have less variance. So we group the coefficients related to the frequency. This is what it is called split the spectrum. We split the spectrum first with the zero coefficients to preserve the average value. Then we take the coefficients with low frequency and split in groups with more or less the same amplitude, and the last 99% remaining are considered noisy. But the best part of this technique is that the 3D cosine transformation is embedded in tNavigator and it is done automatically. And this is how it has to look like when you apply this procedure. You get the permeability in X direction for history matching. It has to be equals to the mean value plus variable plus times in another coefficient plus variable times more coefficients, and so on. The coefficients were grouped depending on the spectrum, and the last part of the formula represents the 99% of the coefficient. That is basically what we call noise. So a brief a brief explanation of the model we are going to see. We have a model close to B match in liquid rate, and the typical way of thinking for such model is that the improvements in oil and water production matching could be achieved through the adjustments of relative permeability curves. If all required relative permeability modifications are applied, they may start to be in conflict with the data measured in lab. So we assume we cannot modify relative permeability curves, and that's why we are going to work with the 3D absolute permeability distribution. So let's move forward to the demo. What we are going to do here is create a project in Model Designer. I'm going to call it Webinar. And after creating the project, what we are going to do is import a data file that already built with all the information related to the grid, properties of the grid, PVT, scale data, history, wells, everything. So as you can see here in a 3D windows, what I'm going to plot is permeability in X direction, and I will just show only the active cells. Create a filter for unknown cells, and this is the model we are going to present. These are the three permeabilities, original permeabilities of the model, and I'm going to duplicate these permeabilities in order to keep the base permeabilities as the original data. And we are going to work with the permeability along X, along Y, and along Z in order to change these values and run the simulations. So as you can see, here are the copy of the permeabilities, the original permeabilities, and we are going to work now with the expand the grid properties in cosine. We're going to tell how many variables we want to have, change the name that we want as an output, and the prefix we want to have. Just by pressing OK, you will see that many new arrays have been created with different permeabilities, and these permeabilities are the ones we are going to use in the formula. This is done automatically in tNavigator. So let's go to workflows. And in workflows, we see all the variables that were created and the formula of the cosine transformations, where we have the values and the different permeabilities already created. Now we are going to copy permeability in X in Y directions and do the same for zeta plus times 0.1 in order to reduce vertical permeability. We run the workflow, and now we have almost the same permeability as the beginning. We need to do the initialization of the model in order to run then the assisted history matching project, where we are going to do the sensitivities and then the optimization of the model. So we create a project for a sensitivity. I'm going to call it cosine sense. Press OK. I need to save the project. And we get these windows where I see all my variables with the minimum and maximum values. I will use a Latin hypercube, tell to run 20 cases and change the minimum and the maximum of the values from -3 to 3. But before accepting this experimental design, I will tell how to run the simulations. I will ask to run 2 simulation models at the same time, also to use the GPU in order to accelerate the simulation. I just press OK, so all the cases were created and they are now running. As you can see in the task manager in my notebook, I have 8 processors, and they are the 8 of them with the usage 100%, and you can see also the CUDA cores that are being taken into account for accelerating the model. In project info, you have all the variables and all the variants of the cases, and in calculations, you can see all the cases that were created that are being calculated. And since it is already connected to Model Designer, you see that it's running also the workflows in order to create the several permeabilities in X, Y, and Z directions. So every single case that finished, we can see them in the results pane. And of course, we can plot, like, for example, oil rate, water rate, or cumulatives for oil and water. Let's move forward and create the objective function that we are going to use for matching the oil rate and water rate. So we are going to use 2 terms, one for oil rate and we for all the wells, and we are going to add the weight of the wells by oil total. The same for water rate, and weigh the wells by water total. Since oil total is more important and it's a little bit more difficult to match, we are going to give a higher weight for oil rate. So as you can see, the model is, the cases are still running. And after we run the 20 cases we told assisted history matching to run, we are going to do some analysis like a Pareto chart to analyze what are the most important variants in our model. And also we can see in a table what is the values of the objective function in order to in a fast way find the best case for our study. As you can see, now we have a column called objective functions and the values of each objective function of each case. And in a cross plot, we are going to see the objective function versus model positioning list. You see that all the cases are coming after they finish, and now I will accelerate a little bit the demo in order to get the 20 cases plot and finished. With this experiment, we see that we cover all the possibilities: oil rate, water rate, oil total and water total, and we have the 20 cases finished. So in the histogram, we can try to find out which ones are the worst cases to take them away from the analysis of the Pareto chart. And we are going to filter those variables in order to create filters of variables, and then run a optimization. So let's create a new optimization with a simplex method. Again, we are going to change the minimum and maximum of the variables, select an objective function, the one we have created, and then select the variables we are going to take into account for the optimizations. All the rest remains with the base value. Now, as you can see, there's a couple of variables and only a few cases that are running. Around 30 cases took to do a more or less nice matching, and we have to do the analysis again for the new cases that are coming. Let's organize the cross plot from maximum value to minimum value to see how the objective function value is decreasing once the cases are appearing. Okay? So now I'm going to accelerate the video once again, and we see that the value of the objective function is decreasing. We got to a point where we got example or case 23 that we are going to use that one. Let's plot this to compare here in the assisted history matching project the results. For example, oil rate, and tick all the cases and just plot the best case. Historical value with the best case we got, and water rate. They're pretty close. So right click in the case and set these variables into the workflow. I need to close the dynamic model because we're going to run the best case in Model Designer and then the base value, the base case. So as you can see here, we bring the base value, the values of the best case. We run the model, the workflow, and we are going to compare both 3D properties of permeability. In the left side, we have the best match, and in the right side, we are going to plot permeability base, the original permeability. So it's not that far from the original grid, but we have some changes. Let's create now the cases. So we are going to run the match case. I'm going to call it dynamic model. I'm going to use the permeability in X, Y, and Z directions and run the model. Let's create a template in order to compare the results from the base case to the solution. So let's plot oil rate and oil rate history and water rate calculated and history. Now we need to run the base case to compare how good was the results with the original case. So let's duplicate the case and use the original permeability in X, Y, and Z direction. Let's change this. Let's move to graphs. Let's tell what to plot. And in this case, we have the first case, the best scenario, and now we are running the original case. And as you can see, there are some differences between the rates from one case to another one. So with just a couple of clicks, we have a better understanding of what is the permeability distribution for doing the history match. So as a summary, with tNavigator, you can take advantages of the integration between building a model, running simulations, running sensitivities and optimizations, your model to match the history of the field. tNavigator's fast simulation speeds allows you to run many more cases in less time to achieve your goals. And you can also take advantages of a unique solution in the market like a discrete cosine transformation. So if you have any questions.
Wonderful. Thank you so much, Horatio. Thank you for everyone for your time and attention today. For your reference, this webinar is recorded and you'll be able to view it in the coming days on our RT Europe YouTube channel. Now we're just going to take a few minutes to answer some questions from the audience. If you have a question that you haven't typed in yet, still feel free to put it in there and we will email you your response to your question at a later time. So to get started, I'm just going to hand this over to Nestor Hernandez, one of our reservoir engineers in the Calgary office. We'll get started with the first couple questions that have come in. Nestor.
Thank you, Jessica. Hello, everyone. So I'm reading here the questions that you're writing. And there's one which is very, very interesting. It's in addition to permeability, which other parameters can be used for DCT? Well, thank you for that question. But many parameters are suitable for DCT method. For example, net to gross is one that could be used. Also endpoints, and even you could use porosity if the geologist that is in your company is okay with playing with the original pore volume. Now, please note that discrete parameters like phase type, like SAT-num, PVT-num, and any other regions that are like discrete parameters, those are not suitable for DCT because the nature of the method, of the mathematical method. Okay, let me see another question here. There were a few small permeability values after the match. Is there any way to set limits? That's the question. Well, yes, that's a very good question, actually. We could set up additional steps to the workflow to set limits for permeability. For example, we could apply a minimum value if the perm is below, say, 0.1 millidarcies by adding an if statement at the end of the workflow. Even you could try to set ACNUM equal to 0 if the permeability falls below a certain low permeability value. So that could be added to the workflow as well. And basically with workflows, the sky is the limit. Like you could do anything there. There are more questions here, but I think we're getting short of time. So Jessica, I'll give it to you. Thank you.
Wonderful, thanks, Nestor. After this presentation has concluded, we will leave it up for just a couple minutes if you're still typing a question, so no rush on that. Thank you all again. Stay safe and stay healthy, and we hope to see you at our next webinar next week on Tuesday, May 26th at 800 hours UTC. Our presentation on Tuesday will be on well placement optimization. So I hope to see you guys there. And thank you very much, everyone. Stay safe.